Have you ever pondered upon the vastness of the universe and the existence of exoplanets? Today, we're going to dive into this cosmic ocean and explore these fascinating questions. The universe, a glittering expanse of galaxies, stars, and planets, stretches out in all directions, seemingly without end. It's a mind-boggling entity, so vast that it defies comprehension. Within this infinite cosmic theater, there's a particular class of celestial bodies that have captured our curiosity: exoplanets. Exoplanets, or extrasolar planets, are planets that orbit stars beyond our solar system. They're like the distant cousins of Earth, Mars, and Jupiter, living in other stellar neighborhoods far, far away. Just imagine these celestial bodies could be swirling with winds, bathed in starlight, or even teeming with alien life forms. The possibilities are as infinite as the universe itself. For centuries, these exoplanets remained hidden in the depths of the cosmos, elusive and mysterious. But with the advent of modern technology and scientific ingenuity, we have begun to pull back the cosmic curtain. Scientists have been using various methods to study these celestial bodies, peering billions of miles into space to uncover their secrets. Through powerful telescopes, intricate calculations, and innovative techniques, they have started to map this vast exoplanetary landscape. As of today, we know of over 4,000 confirmed exoplanets, each one a unique world waiting to be explored. But here's a question that might be lingering in your mind. How do scientists sitting on our tiny planet manage to detect these far-off celestial bodies? The secret lies in a phenomenon called the Doppler effect. So what is this Doppler effect that astronomers find so useful? Well, let's dive into it. Imagine you're sitting in a park enjoying a sunny day. Suddenly, you hear the distant wail of an ambulance siren. As it approaches, the sound seems to change. It gets louder, yes, but it also gets higher in pitch. As it passes by and moves away, the sound lowers again. This change in pitch is a perfect everyday example of the Doppler effect. The Doppler effect is a phenomenon that occurs when a source of waves, sound waves, light waves, anything like that, moves relative to an observer. When the source moves towards the observer, the waves get compressed. They become squashed together, which results in a higher frequency or pitch. When the source moves away, the waves get stretched out, decreasing the frequency or pitch. Now, let's take a leap from the park to the cosmos. We're swapping ambulance sirens for starlight, but the same principle applies. You see, light is also a wave, and it too can be affected by the Doppler effect. When a star is moving towards us, its light waves get compressed, which makes the starlight appear more towards the blue end of the spectrum. This is called a blue shift. Conversely, when a star is moving away from us, its light waves get stretched out, making the starlight appear more towards the red end of the spectrum. This is known as a redshift. But let's not forget, the universe is a busy place. Stars don't just sit still, they move, orbit, twist and turn. This constant stellar dance can cause a star's light to shift back and forth between redshift and blue shift. By observing these shifts, astronomers can deduce a lot about the star, including whether it has any planets orbiting it. So the Doppler effect is not just about sirens and racing cars, but it's also a key to unlocking the mysteries of the universe. Now, you might be wondering, how does this Doppler effect help in detecting exoplanets? Well, it's quite an intriguing application of this phenomenon. You see, when an exoplanet orbits a star, it doesn't just go around in a neat circle. The star and the planet both orbit their common center of mass. This causes a tiny but detectable motion in the star. The star's motion towards and away from us, due to the gravitational tug of the exoplanet, causes the starlight to shift in frequency. When the star moves towards us, its light appears slightly bluer, and when it moves away, the light appears slightly more red. This is the Doppler shift, the same one that changes the pitch of an ambulance siren as it passes by. Now, these shifts in the light's frequency are incredibly tiny, but with precise instruments, astronomers can detect these shifts. By measuring the frequency shift and the period of these shifts, scientists can infer the presence of an exoplanet. They can determine its orbit, its mass, and even get a hint about its composition. But it's not as simple as it sounds. Stars can move for reasons other than exoplanets. They can have spots, flares, or other forms of stellar activity that can mimic the signals of an exoplanet. So astronomers have to be very careful and use additional methods to confirm the existence of an exoplanet. This method, known as Doppler spectroscopy or the radial velocity method, has been incredibly successful. It has led to the discovery of hundreds of exoplanets and has given us a wealth of information about these distant worlds. It's like a cosmic dance where the star and the planet move in rhythm, and we, the observers, decode the dance to reveal the presence of the dancers. Therefore, by observing these tiny shifts in the light from stars, astronomers can detect the invisible, the exoplanets. Beyond just detecting exoplanets, the Doppler effect also provides insights into these distant worlds' atmospheres. You see, the beauty of this technique goes beyond the simple detection of celestial bodies. It allows us to delve deeper into understanding the very air that surrounds these distant worlds. Picture this: the light from a star doesn't just reach us directly. When it has an exoplanet in orbit, some of that starlight will pass through the exoplanet's atmosphere before it reaches us. As the light travels through the atmosphere, it interacts with the molecules and atoms present, leaving a unique imprint on the light itself. This imprint, often referred to as an absorption spectrum, is like a fingerprint of the atmosphere's composition. Think of the absorption spectrum as a barcode. Each line represents a different element or compound. The presence of certain lines can indicate the presence of specific molecules. For instance, if we see lines in the spectrum that correspond to water vapor, we can infer that there's water in the exoplanet's atmosphere. Similarly, lines for methane or carbon dioxide could suggest the presence of these gases. Now, how does the Doppler effect come into play here? Well, as the exoplanet orbits its star, its motion causes a shift in the frequency of the starlight. Remember the Doppler effect? This frequency shift affects the absorption spectrum, essentially stretching or compressing the barcode. By studying these shifts, scientists can not only confirm the presence of an exoplanet, but also gain insights into the planet's atmospheric conditions. Additionally, the Doppler effect can help us understand the exoplanet's wind patterns and weather. Variations in the frequency shifts can indicate changes in the atmosphere over time, giving us a glimpse into the dynamic nature of these distant worlds. In this way, the Doppler effect is not just a detection tool, but also a window to understanding the nature of these distant worlds. It's like having a remote laboratory in space, allowing us to study the atmospheres of planets light years away, right from the comfort of our own planet. So, we've taken quite a journey, haven't we? We began with the vastness of the universe and the concept of exoplanets, those intriguing worlds outside our solar system. Then, we delved into understanding the Doppler effect, that fascinating phenomenon explaining how the frequency of waves, like sound or light, changes based on our perspective. We discovered how this effect can be a powerful tool in the hands of scientists, helping them detect those elusive exoplanets. By observing the slight wobble in the light of distant stars, they can infer the presence of these planets. And it doesn't just stop at detection. The Doppler effect also contributes to studying the atmospheres of these exoplanets. By scrutinizing the light that passes through these atmospheres, scientists can get a glimpse into their composition, potentially hinting at conditions suitable for life. Next time you hear a siren passing by, remember, the same principle is helping us explore the mysteries of the universe.